Now that we've talked about derivatives of regular functions, we did the power, product, and quotient rule, we have to touch on the derivatives of the trigonometric functions. To do this, I'd like you to recall or observe these beautiful graphs of sine and cosine, and remember that the derivative is the slope of the tangent line. In this vein, maybe we can arrive at the derivatives of sine and cosine. For example, if you check out the derivative of sine right here at negative 3 pi over 2, the tangent line is horizontal, meaning that the slope of the tangent here is 0. So the derivative has a value that is 0. Right here at negative pi, the derivative is the slope of this tangent line, which is negative 1. It's again 0. The tangent line has a slope of 0 at negative pi over 2, so the slope is 0 here. At 0, the slope of the tangent line is positive 1 rather, so we have a point on the graph of the derivative right there. If we start to connect these points, you'll notice a pattern for the derivative of the function sine x. Here we have the curve, y equals the sine of x. And in blue, I've graphed the derivative, y prime. You might also recognize y prime, the graph of the blue graph on top, matches exactly the graph of cosine below. At 0, it's 1, at pi over 2, it's 0, at pi, it's negative 1. So, in fact, the derivative with respect to x of sine x is exactly cosine x. Surprising. Let's try cosine. What's the derivative of cosine? Well, at 0, the derivative is 0. At pi over 2, we have a derivative, a slope of a tangent line, which is negative 1. At pi, the derivative is 0 again. So we have these negative values of the first derivative. At 3 pi over 2, the derivative appears to be positive 1. At 2 pi, the derivative, the slope of the tangent line, is 0. So we can connect these slopes of tangent lines and extrapolate to find a curve, and then we would like to know what is the derivative of cosine. This graph looks a lot like the red or purple graph above, but it's flipped over the x-axis. This is negative sine. So we have, as a fact, the derivative with respect to x of cosine x is negative sine x. So to use these derivatives of trig functions, we can put them together with all the other differentiation rules that we know and find derivatives. For example, the derivative of y, we can rewrite 3 over x as 3x to the minus 1 as a power, so we can use the power rule, plus 5 sine x. And from there we can differentiate. So y prime equals negative 3x to the minus 2 plus 5 times the derivative of sine, which we just determined to be cosine. In number 2, to find the derivative, y prime, we'll look at the first term, 5 times e to the x. 5 is a constant, he's along for the ride. The derivative of e to the x is still e to the x, and the derivative of cosine, as we determined, is negative sine of x. So in this way, we found the derivative of combinations of trigonometric functions with other things. In the same vein, we have number 3, where we're tasked with finding the derivative of sine times cosine. So now they're both trigonometric, and they're multiplied together. In this case, we need to use the product rule, where f, the first function, is sine x, times the second function, cosine x. This needs the product rule. If f is sine x, f prime is cosine x, and g prime is negative sine x. So in accordance with the product rule, which says that y prime is f prime g plus f g prime, we can say the derivative of this function y prime is f prime, which is cosine x, times g, regular old g, not fancy, no differentiation of g, plus f, regular f, original f was sine x, times g prime, and g prime is negative sine x. Now we simply need to clean it up. So what's the first derivative? Y prime equals cosine squared x minus sine squared x. So there's our first derivative, using the product rule for sine and cosine. Now you might be tempted to think, oh, I know an identity about this. And these identities are important, trigonometric identities, like sine squared plus cosine squared equals 1. We like to use that. You might also need to know the fact that tangent is sine over cosine and other quotient identities. Also, we have the reciprocal identities, like how we get to cosecant and secant. So if you don't remember that stuff, look at the trig reference sheet that's provided on e-learning and print it out, or use the copy that I gave you at the beginning of the semester so that you can become familiar with these. You won't be allowed the reference sheet on the exam, but it's good to have handy while you're doing the homework, and hopefully with practice you can remember those important things. You'll notice here that cosine squared minus sine squared is not an identity, so we can't simplify that, but we might keep it in mind for future problems. So if y equals the tangent of x, and we're looking for the derivative of tangent, but we only know the derivative of sine and cosine, you'll have to write tangent as sine over cosine. We know the derivative of those functions, so now using the quotient rule, we can find the derivative of tangent. The quotient rule says we need low d high minus high d low. Low times the derivative of high minus high times the derivative of low, all over low squared. The low function is cosine. Derivative of sine, d high, is also cosine. So that's low d high minus high sine d low. The derivative of cosine is negative sine, all over low squared. That's cosine x squared. By simplification, we have cosine squared x plus sine squared x all over cosine squared x. But we remember that this is a Pythagorean identity. Cosine squared x plus sine squared x equals 1. So this is now 1 over cosine squared x. We have another way to write that too. That's 1 over cosine of x all squared, or secant squared. So that derivation for the derivative of tangent holds. It's always a derivative of tangent, and we can do that for other trigonometric functions as well as necessary. So we already determined that the derivative of sine is cosine, the derivative of cosine is negative sine, and the derivative of tangent is secant squared. The same way we did these derivatives, we can find the derivative of the other three trigonometric functions. The derivative of cosecant, that's 1 over sine, is negative cosecant cotangent. The derivative of secant is secant tangent. And the derivative of cotangent is negative cosecant squared. Same way we did the other ones. If you don't remember them, you'll have to be able to invent them on the exam. Notice one thing, and that's that the trig functions who start with c have negative derivatives. That's the derivative of cosine, cosecant, and cotangent. and the other 3 are positive derivatives in sine. But however you do it, make sure that you know these on the exam and then going forward in this class, because they'll show up. They'll show up in things like the next example. Find the derivative of y when y is x squared times the cotangent of x minus 1 over x squared. So now this example shows a lot of the things that we've done in this class. X squared cotangent x needs the product rule, and 1 over x squared needs to be rewritten as an exponent. X squared times cotangent x is product. F is x squared, cotangent is g. We'll use the product rule here when we create y prime. That means that y prime is f prime g plus f g prime by the product rule. F prime g plus f g prime. So what's f prime? The derivative of x squared is 2x. G is regular old g, cotangent. F, left alone, not differentiated, is x squared, and g prime, the derivative of cotangent, is negative cosecant squared. Then we can differentiate this last term. Negative x to the negative 2 is negative 2, or positive 2 x to the negative 3 power. So maybe you clean this up. 2x cotangent of x minus x squared cosecant squared x plus 2x to the minus 3 power. And that's the first derivative. If you have things like this on your homework and they don't match the back of the book, check these trig functions. See if they have the same denominator. Maybe the textbook factored that out. Maybe it would have taken an x out. I really can't be sure. I don't mind them if they're these long polynomial chunks, because if we had to differentiate it again, we might as well start from there.